All right. So we're continuing on in this convection territory. And for a lot of these, kind of like I said last week, though, I think a lot of people were still working on the quiz. The a lot of these things are just kind of calculating the numbers that you need and then finding the equation that works based on the criteria. So I've tried to, on the right side for a couple of these questions, include the parts of the textbook. So a lot of the time what you're going to be doing is calculating Reynolds number, and you can find Prandtl's number based on the properties. And then you use that to kind of narrow down what formula you need. And then there's all these cases. There's some for flat plates. There's some for spherical plates. There's, we'll do one in a bit where most of the plate is heated, but a little part of it isn't. If that doesn't make sense to you, we'll do the example. So it's essentially, because so many of these equations come empirically, so rather than there being knowledge of the empirical heat transfer equation, a lot of them are just developed through testing. And so as a result, there's just kind of all these cases. So in this case, they're forming plastic in a plant, and they have this plate that's 1.2 meters wide, 2 millimeters thick, though I don't think that matters. And it's being put through at a rate of 5 meters per minute. The temperature of the plastic is 9 degrees, so we know the surface temperature. And it's exposed to the 30°C air at 3 meters per second on both sides. And then the width of the cooling section of the fixed point on the plastic sheet passes through that section in 2 seconds. So as the whatever width this is, it essentially means that the whatever width is exposed to this air passing it over means that it's in there for about 2 seconds. So of course, with heat transfer, you're usually concerned with the area that's transferring heat, and so that'll be important for that. Okay, so the first thing we'll do in a lot of these questions is we'll just find the properties of the fluid we're dealing with, and usually we're interested in what the air is like kind of in between where it's caught on the surface and that it's kind of in this infinitely far away thing, or infinitely far away space where we have our, in this case, our temperature of 30 degrees. So, so what we normally do is we take the average temperature, so our T surface plus our T infinity over 2. Which is 90 plus 30. And then we're going to go to table A15. And this is in your textbook, and I won't read everything off the table, but I'll just give you an idea of what it looks like. So it's in the back, and it has all this information on it. So density, specific heat, thermal conductivity, diffusivity, Prandtl number is on there as well. And so we can get all the information we need off of there to get started. Okay, and then often, or actually I'll follow the answer key here. So we're gonna figure out the width so that, like I said before, the amount of kind of area that was under influence by the airflow. So we said width is equal to our velocity times our delta t. So we know how quickly, so this is the velocity of the sheet, not the velocity of the air. So, and so again, this is just going back to the picture. This is just to figure out kind of what this area is, and then we'll get more into the convection stuff. (15/60 meters per second times our 2 seconds is 0.5 meters. Okay, and then usually the first thing we do when we deal with convections, we figure out whether or not we're talking about a laminar region or a turbulent region. So now we're looking at the air velocity. We're using our Reynolds number, and we usually look right at the end of our length just to see the air will always start in laminar. What we're trying to figure out is really if it's going to get to a turbulent flow. So we have 3 meters per second, 1.2 meters. And this we got off that table. And this gives us a Reynolds number of 1.899. Does anyone know what Reynolds number corresponds to turbulent flow? Or does anyone know? Another way of saying is this laminar flow or turbulent flow?
Isn't it for that situation like 5 times 10 to the 5? But we have a table, I think.
Okay, no, you're right though. 5 times 10 to the 5. So if it's less than this, then it's laminar. Do you have a table for this or for something else?
Well, there's a table for the Reynolds number in the book, depending if it's like on the surface it is or in which type of, I'm not sure exactly, but there's different situation that I need to review.
Okay, yeah. There's a lot of there's a lot of tables in this book. I think in general this number is always true. Reynolds number, these kinds of non-dimensionalized numbers are usually meant to deal with a lot of situations. But there would be lots of tables probably for like what equation you use associated with different laminar or with different Reynolds numbers. So.
Sorry, what's for the Reynolds number? What's is it the velocity? The number 3?
Yeah.
Okay. Yeah. So velocity is 3 meters per second, or am I mistaken? Because I think it's
yeah. So 3 meters per second. Yeah. So this question's maybe a little confusing because there's a couple different speeds. There's the 15 meters per minute. This is the rate in which the sheet's moving through. And that's only important in the sense of, because we also know that it's exposed for 2 seconds. And so eventually we'll need the area. And so we use that to figure out how kind of wide this is. So that was our first velocity. And then our second velocity, because this is now talking about the flow, we're referring to the airflow.
Okay, and the airflow is mentioned in, it's mentioned in the problem.
Yes. Yeah, so it's also mentioned here, but I went over that quite quickly, so it's good to clarify. Okay, so now that we know it's laminar, we can find our nuisance number, which is related to our heat transfer coefficient. And for laminar, we have one flow. For turbulent, we have one flow. And all of these are for only only for a flat plate and only with a uniform surface temperature. So for other situations, you'll have different equations. So it's a matter of familiarizing yourself with which ones matter. But once you know you have this, you know you have your Reynolds number less than 5, your Prandtl number is greater than 6, or greater than 0.6, sorry, which is true here. Then you know you can use this equation, and then from there it's fairly straightforward. So our Nusselt's number, which is HL over K, 0.66. All right, and this is equal to 259.3. Again, this is dimensionless. Okay, so now we just rearrange this because what we're interested in is our heat transfer coefficient. Okay. And in this question, we're trying to find total heat transfer. Oh, I see a chat. Oh, thank you, Karina. Table 7.1. Oh, for different cross sections, yeah. Okay, that's good. Is that does that table have just equations, or do they give you numbers as well? Both. Okay, cool. All right, that's useful for everyone to know in the chat. Okay, so okay, so our area of our surface is equal to 2LW, and this is where we use this width that we found earlier. 2 times 1.2 times 0.5 is equal to 1.2 meters squared. And it's just 2 because it's on both sides. So normally you just would calculate the one area. And then now we can figure out total heat transfer. Actually, save some time and write it all out. We found H, we have our area, we know our two temperatures. So we can calculate this as 437 watts. Okay, and that's it. So this question's fairly straightforward. And again, it's just a matter of knowing kind of which equations to use in which case. So this one was the flat case constant temperature. The next one will also be similar, but the next one's going to show a little bit more about, I guess, what these H's are. But I guess first, any questions on this problem?
Can you show the answer, the heat flux answer again, please?
Yeah, sorry, I know I move away quick. All right, is that good? All right. Okay. So in this question, it's a similar one. So we have parallel plates. So we have flat plates on the roof of this house, and we have our velocity and our temperature going over them. So the plates are maintained at 15 degrees Celsius. So we have a similar situation. We have our surface temperature, 15 degrees Celsius. Ambient air is 10, so we know V infinity, and we know our velocity. And so we want to determine the rate of convective heat loss from the first plate and the third plate. And it took me a long time of staring at this question to understand what they mean by that. So each of these plates are 1 meter long. And so this first 1 meter, this is plate number 1. Then this 1 meter is plate number 2. And then this 1 meter is plate number 3. And the reason why these two are gray is because these are the two that we're trying to determine the heat transfer around. So not the best picture maybe, but what we're going to find is that the longer we kind of, or our H is going to change whether or not we're considering the first plate, the second plate, or the third plate. And the concept there is that if we have a flat plate, we actually have an H for every spot. So we have an HX here, and we also have an HX here. And so what we found in the last one is you can actually take the integral over this and you can find just an average H. And that's actually what we did in the last question. We were just finding an H, we weren't finding an HX. And that's, again, what all those equations that we talked about are useful for. But what we're going to look at here is how the distance changes. So the air comes, and then as it hits the leading edge, it creates this boundary layer. And depending on how far down the boundary layer you are, your H will be changing. So that's the concept. And then hopefully as we go through the question, that will become more clear. Okay, so we're going to do a similar thing to last time. First thing we're going to do is just take our average temperatures. So our average between our surface temperature and our air temperature. And then we're going to go back into our table, A15, and we're going to get all those values that we need to start with.
The first variable, is it K? You wrote that?
Yes. Okay. And then actually, so like I said, for each plate, we're going to have to find kind of a different Reynolds number and all that. Okay, so I think the first thing we're going to find is our critical Reynolds number, because we're going to want to know whether or not at some point our air as it passes along is going to turn laminar or not. Just give us a heads up as to whether or not we're going to have to deal with that. So we're going to find our critical length, which is just a reorganization of our Reynolds number equation. And we know that our Reynolds critical is just this 5. This is when it turns into laminar flow. Sorry, when it turns into turbulent flow. And this is at 3.62 meters. And for our hosts, we're interested in the first plate and the third plate. So the total distance we're ever going to look is 3 meters. And at 3.6 meters is where it turns turbulent. So for this whole question, we're going to be dealing with laminar, which is nice. So the first thing we want to do is just the heat transfer over the first plate. And this one's pretty much the exact same as the last question. So I will go over it quickly. So our Nussbaum number, using that same equation as last time again. So we know Reynolds number because we just calculated it, and we know Prandtl's number because we found it on that table at the beginning of the question. So this is 222.5. So our H is K over L times Nussbaum number. So our area of the plate, so the dimensions were given. We had the height or the dimension of the roof, and then we know that each one of them are 1 meter. So our 4 meters, that's the width of the roof. 1 meter is the size of the panel. 4 meters squared. And then after all that's said and done, we're back to the equation we dealt with in the first tutorial. And save some time, not write this all out. So we have our H, we just calculated, our A, we just calculated, and we know the temperature of our panel and the temperature of our pair. And so we'd get 109 watts. Okay, so a question on the chat from Sarah. Why do we take x equals 0.5, or why don't we take x equals 0.5 on the first plate? Why do we choose to evaluate the Nussbaum number at the last point of the plate instead of the middle point? So that's a good question. And it gets back to again, what we're trying to do here. So the equations in this chapter are the ones we're dealing with are typically not specific to a certain point, but are actually the goal of these equations is to try to find averages. And so it's maybe this is what you mean, is that it might intuitively make sense to find the nuisance number at the kind of midpoint, because that might give you an idea of, on average, how much it's using. But actually that equation is built with the intention that if you use your x as 1 meter and you look over the whole length, then, and you find, I guess, your Reynolds number there, then you are going to end up with an average h for this whole length. Okay, perfect. And so that's important, because as we then look longer, so as we add on, so this was our one plate. So as we add on a second plate, our h at a specific point, again, is going to change. And so what we're going to want to do is we're going to want to look at our Reynolds number across the whole distance, across the two plates, and then again across the three plates would give us, and by looking across all three plates, we would get our average h for this whole section. And just to remind you, what question B asks for is just the heat transfer from this plate. So if we use the whole distance, then we're going to find our average h across this whole section. And that's actually not going to be the same as the h that's just for this section. But we're also a little stuck here because we can't just use the Reynolds number at our 1 meter again, because our h started to develop here. And so by the time it's got in here, the flow is already developed over these three plates. And so it's not like it's starting a new plate. And so the solution that we come up with is we essentially find our heat transfer that occurs between here and here, because we're pretty good at starting right at the beginning. Then we're going to find our heat transfer that occurs across the whole thing. And then we're going to subtract the two. So all that was the first part. I'm not sure if I wrote A up there, but now we're doing B. So we're going to find, again, we're going to find the average h over the first two plates. So we're going to find our Reynolds number. We'll call this 2. And in this case, it's nice because the 2 refers to 2 meters, because so our 2 meters per second are 2 meters across our two plates, and then divided by our viscosity. Sorry. All right, and then we find our Nusselt's number again, same equation. And you notice the Reynolds number is subscripted 2 because we're talking about our second plate, but our Prandtl number stays the same because we assumed a constant surface temperature throughout the whole thing. Or I guess we were told in this case. And I'll skip some of the intermediate steps here just in the interest of time, and because we've seen this calculation a couple times. So now we're using the same K. Our length this time is 2 meters, and the Nusselt's number is what we just calculated. All right. And then using that, we can find our Q. This is across our first two plates. H, that H2 we found, the A area of the two plates, which is 2 meters wide. Ts minus T affinity stays the same for all of them. Okay, now we need to do the whole process. We're going to find Q1 to 3, and then we're going to subtract the 2 to find just our Q3, which is what we're looking for. So our Reynolds number 3, same equation, except this time we'll use our 3 meters. So now we're getting close to the turbulent region, but we knew we wouldn't get there because we calculated our critical length at the beginning. And if we did get into the turbulent, it would be just a different equation that we use. Nusselt's number, same technique as last time. H, also the same technique as last time, this time using a length of 3 meters. And our Q, and this is our Q1 to 3, so across the whole length. On the next page. Be 189.5 watts. So that means our Q3, and for all of these, I should have had a dot on top, so we'll correct that in a second, is equal to our Q1 to 2, sorry, Q1 to 3 minus our Q1 to 2, which is equal to 34.8 watts. All right, and if we compare that to our other one, 109 watts, so you can see that as the air moves down the surface, just of the nature, because of the nature of how the flow develops, you end up getting less power out of the third one.
Sorry, bro. For the Q1 to 2, what area do you use? Is it the same as the one before, or is it a much larger area because of the two plates?
No, it's sorry, for the Q1 to 2.
Yeah, for the Q1 to 2 and Q1 to 3, is it the same area you use all the time, or is it the area getting bigger because there are more plates included?
The area is getting bigger. So this area would be 4 meters. That's the length of the roof, times 2 meters because we have 2 panels, and each panel is 1 meter wide. And then this Q, I didn't show the area, but this Q is calculated with our third area, which is the 4 meters times the 3 meters. Does that help?
Yes, that's perfect. Thank you.
Okay, awesome. All right. So that just hopefully helps you understand a little bit that this H, it really does depend on a lot. So at the beginning of the course, when we were just given that, depends on the flow, it depends on the surface. It also depends on how long the edge is, the temperatures of everything. So it's quite a complex thing. But we actually have the tools to solve it for a whole bunch of different situations. So I don't think we're going to get all the way through our question 3, but I just wanted to show you because it is a slightly different situation. So we'll at least start it and kind of get the equations in. So we have another long flat plate. We have 50 Celsius water vapor that flows in parallel over a 2 meter long flat plate. And there's an unheated starting length of 5 meters, and there's a heated section, sorry, 0.5 meters, and there's a heated section with a surface temperature of 250. And so we want to find the local convection heat transfer coefficient at x equals 2 meters. So we want to find the local one, the average convection heat transfer coefficient of the whole section, and the rate of heat transfer per unit width of the heated section. So hopefully now we kind of understand the distinction between what the two is asking. The first one is asking for hx at 2 meters, while the second one is just looking for h. So in the last two questions we were finding h. So this sounds kind of tricky because we have this 2 meter flat plate, but we have this half a meter that's not being heated. But like in a lot of things in this course, we actually just have this very specific case. So there's a section of the book, flat plated with an unheated starting length, and we're able to find our Nusselt's number and our h for each one. And they say that there's many practical applications for this. So what we're learning is kind of the ones that are common. And so what they're saying is that we have this situation, and the last one we were saying as the flow developed along the plates, the H changed. And this is just a situation where your kind of temperature or heat transfer might actually develop after your flow develops. And so again, just a specific situation for that. So we'll try to get some of the equations down in the limited time we have. So the first thing we're going to do is we're going to find our Reynolds number, and we're going to find it at x equals L. And again, we're finding our Reynolds number at our full length, even though the first 0.5 meters is unheated. And that's just because our Reynolds number is talking about the flow, and the flow starts to develop right at the beginning of the plate. So we have our
Sorry, what number question? What question number is this?
This is, doesn't say here. It will be 7-57. This will be in the newest edition. The other question numbers in the past were in the 5th edition because it's the one I have access for, but this one I couldn't find in the 5th edition.
All right, thank you.
Okay. 3.564 times 10 to the 5. So once again, we have laminar. So we know we just use the equations for laminar flow. All right, so now what we want to find is our local heat transfer coefficient. So what is our H at x is equal to L? The point I've tried to drive home is equation. Okay, so the part that's missing here is that our Nusselt's number is equal to sorry, I'm missing what we wrote earlier. HL over K. So because this is NUX, we can say that this is equal to HX L over K. And so to find our hx, if we find our useful x, then we use this equation and we'll find our hx. And then what's of more interest to us is our h. Again, that's the one that's the average. And so what we do is we find our h all the way at the end, and then we just correct it using this equation. And this equation looks slightly scarier than it is because this symbol just refers to the length of the leading edge. Okay, and we're out of time, but if you were to continue, you would find, yeah, here I can just try to guide you so that it's in the notes. So you'd find your Nusselt's number of x using your Reynolds number, which we now have. Reynolds number you'd look up, length of the leading edge you would know, and then x, since we're looking at our full length at x equals L, you would just put in your L there. You would have your Nusselt's number. From there, you could find your convection coefficient at x is equal to L. And then once you have your local convection coefficient at x is equal to L, you use this equation to find your average coefficient equation, just H. Okay. Any questions about that?